In this video, we're going to talk about motion purely in a numerical sense. We are going to be calculating, and a lot of this lesson is going to look pretty much like a math algebra class. But our primary topic today is the kinematic equations. When I say kinematic equations, I'm talking about a system of equations that will allow us to calculate for any unknown in a motion problem that we come up against. Now, before we can get into the kinematic equations, let's talk about the 5 main motion variables that are going to be relevant for us in this unit. It's displacement, initial velocity, final velocity, acceleration, and time. Now, each of these variables or each of these properties has its own variable letter to represent it. And in IB, it's going to be a little bit different than maybe what you've seen in past classes or what you might see in any other class that you're going to see in college. So let's go through the symbols that are used in an IB data booklet. First, time, pretty straightforward. We're going to represent that with a lowercase t. Acceleration, same thing. It's going to be just a lowercase a, pretty much what you'd expect. And final velocity is going to be a lowercase v. Now here's where the variables get a little bit different than what you might expect. Final velocity is what's taken our v, so we can't use v for initial velocity. Some courses might use vi or vf for initial or final, or v1, v2. In IB, we're going to use v for final and u for initial. And I know that's kind of weird that initial velocity doesn't have a u in it at all, but we'll use u for initial, v for final. And then finally, our displacement is also something different than what you might expect. We're going to use the lowercase s to represent displacement. Not a d, but s. Displacement is different than distance. So I will lovingly refer to these as the SUVAT variables in this class, as just a reminder of the 5 different variables, and it spells the word SUVAT. Knowing all 5 is going to become really useful in our problem solving process, because we can account for all the different variables, and then if any are missing, that will help us determine what equation to use. So the first main variable that we're going to talk about today, and really the whole point of the kinematic equations, is this idea of accelerating motion. In our last classes, we were talking about how you can define motion using a displacement graph or a velocity graph, and then looking at if the velocity is changing, we call that acceleration. We can define that based on the rate of change of velocity. Now here is our primary numerical or mathematical relationship for acceleration. It's just the final velocity minus the initial velocity over time. It's the rate of change of your velocity. So acceleration in symbolic form is an a, final is v, minus initial is u, divided by the change in time. If I were to do that using units, I would say meters per second minus meters per second. That will give me meters per second as a result. Divided by seconds again will give me meters per second squared, also known as meters per second per second. Notice here I'm using this negative exponent notation. If you write that as a fractional quantity, that's totally okay as well. Meters divided by seconds squared is reasonable. So you can see that here. Now, we've talked about this unit already, and the fact that the unit itself comes from the idea of slope, that the slope here is going to be giving us how fast the velocity is changing. We go from 0 to 40 meters per second in 4 seconds. That's a slope of 40 divided by 4, 10 meters per second every second, or meters per second, meters per second squared. Now, the way that you can remember this is slope is just the change in y over change in x. Y is meters per second, x is seconds, so meters per second divided by seconds again will always get you this unit for velocity or for acceleration. In IB, like I said, we're going to be using this negative exponent, but you can use the other ones. I will know what you mean, IB will know what you mean. This is just how it's presented to you in a problem from here on out. So if we wanted to try this in a just a word problem, it would look something like this. Very simple example. what is the acceleration of a car that accelerates from 15 meters per second to 35 meters per second over a time of 10 seconds? Now, it's really, really useful in this class to list your variables. I'm not going to expect you to do any sort of problem-solving strategy where you're listing and then writing the equation and then doing so in just a rote way. But something I always expect you to do is list the variables that you know. This is more for you than it is for me, but it's a great way to communicate kind of where your understanding of the start of this problem is going to be. So we're going to take our 15 meters per second. That is our initial velocity. Our 35 meters per second is our final velocity, and 10 seconds is the time. I'm just putting a question mark here for A. The acceleration is what we're looking for. As a reminder, our equation is A is equal to V minus U over T, which, plugging in our values, 35 minus 15 divided by 10 is 2 meters per second squared. We can look at this in another example as well. Find the average acceleration of a northbound train that slows down from 12 meters per second to a complete stop in 8 seconds. Again, we are looking for the average acceleration, so I'm going to put a question mark next to A, because that's what we are looking for. Next, plug in what we know. We know that it slows down from 12 meters per second to a complete stop in 8 seconds. A complete stop in this case is going to be 0 meters per second. So even though it doesn't give you the number 0, you should know enough to plug that in. Know that your final velocity, V, is 0 meters per second. And then your time in this case is 8 seconds. Again, our equation is A is equal to V minus U over T. Plugging in what we know, the final velocity, V, is 0. The initial was 12. And then 8 is our time, which gives us a negative 1.5 meters per second squared. This negative is important. It just means that in this case, if the velocity was positive and it's slowing down, then our acceleration must be negative. That's that opposite direction to cause this slowdown. So it is okay if it's negative. That's important. Don't get rid of it. It has meaning. So make sure that you keep that if that's there. All right, so that was one equation. But this equation actually isn't given to you anywhere in your IB data booklet. So you're not given this equation looking like this on your IB exam. But you're actually given this equation just in a slightly different form. I would like you to go ahead and solve this equation for the variable V, the final velocity. So if you do this, and it might be useful to do it on a piece of paper, just multiply both sides by t, and then add u to both sides, and you end up with v is equal to u plus at. This equation is given to you in your data booklet. This is the first one that shows up. As we're going to go through these different equations, we're just going to plot them where they are. This is just a snapshot of what your physics data booklet is going to look like. This is just one small part of a larger booklet. But here you can see this first equation showing up here. These are our 4 kinematic equations that we're going to talk about today. Now, for our second kinematic equation, we need to reach into something that we talked about in the last video on calculating from a graph. There are a couple different ways that you can figure out how far you've gone if you know your velocity and you know your time. The first of which is just to calculate. So if velocity is distance or displacement divided by time, the displacement, or the distance, is just velocity times time. 80 meters per second times 10 seconds gives you 800 meters. Now, that kind of makes sense if you think about it. You're growing 80 meters every second for 10 seconds in a row. You just say 80 times 10, and you'll get what you need. We also talked about another method in the other class period, and that is you can find displacement from a velocity graph by finding the area under the curve. So here we have a base of 10 seconds, a height of 80 meters per second in this rectangle. So the area under this graph is also 80 meters per second times 10 seconds, 800 meters. So that's a good reminder to us that these graphs can tell us more. If you have a displacement versus time graph and find the slope, you know the velocity. If you know the velocity time graph and you find the slope, you know acceleration. And then if you have this velocity time and you find the area of that, that can help you find the displacement. We're going to use this strategy to derive equation number 2 in our kinematics. Now this was a little trickier. You won't have to do this on a test, but I think it's useful to know where it comes from because you actually know the strategy already. If I gave you this problem in a graphical sense, basically saying that you started at 20 meters per second and then you sped up to 100 meters per second over this 8-second span, the area under the graph here to figure out how far I've gone looks something like this. This is a trapezoid. You might know the formula for a trapezoid, or you might want to split it up into a rectangle and triangle. There's also another way that's kind of a clever way to find this in an easier area. We just slice off the top and then we slide it down there so it makes it a rectangle. Now, if I do that, I end up with a rectangle that has 8 seconds as the base and then 60 meters per second as the height. And I can find the displacement from that. 60 meters per second times 8 seconds is 480 meters. Now, that's great in this case because I just read it from the graph, but it's not an easy way that will work for necessarily every problem. Instead, let's come up with a generic formula that will help us no matter what that graph looks like. As long as we have a consistent acceleration here, this 60 meters per second is just the average between where we started and where we ended. So if you average 20 and 100, you would end up with 60 because it's halfway in between where you started and where you ended. This average velocity, in a symbolic sense, would be v plus u divided by 2. So you add up and then divide it by 2. That's how you find the average of any two numbers. So if I know that that average velocity will always be the height, I can just multiply that by the time and figure out what the area under the graph, the displacement, is going to be. So generically, I can say S, the displacement, is equal to this average velocity, v plus u over 2, times the time. I can rearrange this slightly to form our second kinematic equation that we're going to be dealing with today. It's this one right here. So all that's happened is we just multiplied that t in and put it on the top part of that fraction. So this is equation number 2. To get equation number 3, you're actually using that second equation, but you're going to take out the v. So if I had this equation, but I didn't actually know what the final velocity was, I can do something clever using that first equation. Because I actually know another way of calculating the final velocity. V is equal to u plus at. If I plug this u plus at in instead of v, I get this. S is equal to u plus at plus u times t over 2. So this red is just a substitution that I made. That's equivalent. Okay, I'm going to simplify that out. These u's can be combined. So I end up with 2u plus at times t divided by 2. I can simplify that further, multiply that t into each of those terms, and divide by 2. Still, I get 2ut plus at squared over 2. And then simplify that out. The 2's cancel, and then I end up with 1/2. So this is our third kinematic equation. S is equal to ut plus 1/2 at squared. You will not have to derive this on a test ever. Instead, it will be given to you because it is also here in your data booklet. This is the equation that shows up right here. So now we've done the first one, the second one, and the fourth one. This third one is also derived from smashing two equations together, but just for the sake of time, let's just take my word for it. I don't like to do that typically, but this is also combining two equations to get one final possibility. So we put them all together. These are our 4 important kinematic equations. Now you'll notice that all of these have some combination of those 5 SUVAT variables. So you might be wondering, like, why would I need 4 equations if these are all dealing with the same variables? Well, if you look closely at it, you'll notice that each of these has a different combination of 5 variables. So this first one uses u, v, a, and t. Second one uses only s, u, a, and t, and so on. Each of these is missing one of the 5. That is going to become really important for us to know how to use these equations to solve some problems. So let's put these in action. This is the stuff that you are going to have to do more commonly in this class. So let's say you have a speed, or you speed up from with a uniform acceleration from 0 to 30 meters per second in a span of 5 seconds. How far have you gone? First, let's list our variables. I just like to write out all of them, SUVAT. And then I just list in what I know, and then what I don't know is going to become useful to me later on. So here I see that we start at 0 meters per second. So first we're going to be looking for displacement. How far have you gone? So S is what we're trying to find. U then is 0 meters per second. V is 30 meters per second. And then T is 5 seconds. Notice here, I have one variable that I'm looking for, 3 variables that I know, and then I have this other variable that isn't in this problem at all, besides knowing that it's uniform. I'm just going to put a dashed line or an X. I don't need that variable to solve this problem. All you ever need is 3 variables to find a 4th one. Okay? Why this is useful is there is only one equation in this list that does not use A, but uses everything else. And that's this last equation here. And you'll notice it's already solved for S. So we're just going to take that equation, plug in the variables that we know, 30 meters per second plus 0 seconds, times 5 divided by 2 will give us a total displacement of 75 meters. I can do this in another example as well. If a plane on a runway is accelerating at 4.8 meters per second squared for 15 seconds before taking off, how long should the runway be? Again, I'm looking for a how long here. That is telling me displacement all the way. How should I plug in from here? I've got acceleration of 4.8 meters per second squared for 15 seconds. I'm looking for 3 variables that I know to solve for this one unknown. But it looks like I'm accelerating at this time before taking off. I imagine that this plane, if it's taking off, is starting at 0. It's starting at rest. So I'm going to make that assumption and say that U is 0 meters per second, which means I don't need V. I don't need the final velocity. Go ahead and identify which equation am I going to use here. So looking at these possible equations, the only one that doesn't use V is this one right here. This one, it says S is equal to UT plus 1/2 AT squared. You'll notice I have everything except for S, which is going to allow me to solve for that unknown. I'm going to plug in what I have, 0 times 15 plus 1/2, 4.8 times 15 squared. Honestly, I wouldn't have to write this UT part. That's going to cancel out to 0 anyway, and that will give me 540 meters. Alright, one more example here. Let's say that a driver slams on the brakes and skids for 3 seconds before coming to a stop. You go and measure that skid, the skid marks show a deceleration over 9 meters. So the skid marks last for 9 meters. What was the initial speed of the car? Alright, I'm looking for initial speed. Remember this U and V. U is the initial, V is the final. So I'm looking for U in this particular case. The things that I know that the time is 3 seconds. I know that the deceleration happens over 9 meters, and I know that I came to a stop. So even though it doesn't say anything further, I know that V is going to be 0 meters per second. In this case, I don't know A. Which equation will I need? So if I don't know A, there's only one equation that doesn't use A. That's this final one. I'm going to plug that in here. Now, this equation is not solved for what I need it to solve for. I want it to solve for U. I want to find U, but this is currently solved for S. So I'd like you to take a piece of paper or sketch on Notability or somewhere else. I would like you to go through and solve for this problem. I would like you to figure out what is the initial velocity, what's the initial speed of that car. So hopefully you had a chance to plug that all out. I like to rearrange beforehand, but I am not going to dock you points in this class if you plug in variables first and then rearrange. But you really got to be careful with how you're rearranging on some of these. So here, I would multiply both sides by 2 to get 2s, divide both sides by t, so it's 2s over t, and then subtract that the final velocity. And plugging in my variables for what I know, I know that s is 9, t is 3, and then the final velocity is just u. Our final velocity is just 0. So our 2 times 9 over 3 is 6 meters per second. Alright, so with all of that in mind, really the key takeaways are kind of along the same lines. One big concept here. You should be able to identify these SUVAT variables, the 5 primary variables, especially knowing that s is displacement, because that's different than what we've probably seen, and then that u and v, initial and final velocity. You should be able to identify the proper kinematic equation to use based on the problem. Remember, the best way to do this is to identify which variable is the odd one out. You know 3 of them, you're looking for 4, the 4th one, and then the 5th one is just unneeded in the problem. Cross it off and use that to figure out which equation you need to use. You should be able to rearrange to solve for an unknown variable, and then, of course, calculate for that unknown.